Let's get started with lecture 10. So a brief review of what we did last time. We started talking about the kinematics of simple harmonic oscillators. So review simple harmonic oscillator. So we said it's periodic dynamics with a sinusoidal form, which in general we can write as x of t. For example, if we're thinking about the position of a particle being described by a, which was the amplitude, the maximum displacement, times cosine omega t plus phi naught. Cosine goes between -1 and 1. Phi naught just tells you where you are at the beginning when you set your clock, when time is equal to 0, what is the position and what is the velocity. And omega was related to the period, right? So if we have as a function of time, if our x of t looks like this, some oscillatory function of time, the amplitude is this height here, so it oscillates between a and minus a because cosine is between 1 and -1, and the period is the time it takes to have one full cycle. So what comes after this point is the same as what comes after that when you just go down. So that time we call the period. And we said, well, when we add capital T, the period, to the time, we want nothing to change. So we want to add 2 pi to the argument of the cosine. And then omega, therefore, is 2 pi over t. We also define the period to be just 1 over t, so that's the number of cycles per second, which is the inverse of the time for one full cycle. All right, so we had these. There was the geometric way of visualizing this motion, which was thinking about circular motion where you rotate around the origin with constant angular velocity omega. So let's say you start at some angle phi naught and you keep going. And then we can think of, well, then this angle phi at some later time is just phi naught plus omega t. And now if the radius is a in this circle, the projection on the x-axis is our x of t. All right, so that's quite helpful in problem solving when we have this type of sinusoidal simple harmonic motion. A couple of other things we did was talking about velocity and acceleration. So if x of t is that, v of t is just a derivative with respect to time, so that turns out to be minus a omega sine omega t plus phi naught. Taking another derivative, we found a of t to be dv dt, and that's minus a omega squared cosine omega t plus phi naught. So we'll see that the maximum velocity or the maximum speed is a times omega, maximum acceleration is a times omega squared. The acceleration is just proportional to the displacement. So that's another useful expression, which when we talk about dynamics, talk about what type of forces would give rise to simple harmonic motion. You can already see that because F is equal to ma, a force that's proportional to the displacement would give rise to simple harmonic motion. But we'll come to dynamics a bit later, and we discuss it in more detail in various contexts. All right, so we left the last lecture with a problem. Let's go over this problem together. So we have an object on a spring that oscillates with a period of 0.8 seconds, and the amplitude is 10 centimeters. So let's write these things. So we have, so that's example 15.3. So A is 0.1 meter, right? It was 10 centimeters. The period was 0.8 seconds. What else do we have? All right, so we know at t equals 0, it's 5 centimeters to the left of the equilibrium and moving to the left. And we want the position and the direction of motion at t equals 2 seconds. All right, so this circular motion picture is quite helpful. So let's draw a circle here. So we know that at t equals 0, if I draw my circle, it's a circle of radius 10 centimeters, the amplitude. And at t equals 0, it's 0.5 or 0.05, half of the radius, meters to the left of equilibrium, and is moving to the left. So it's here, right? So the projection is going to be here, where this is 0.05 meter. So if the projection is here, the angle on the circle, the angle phi naught, if we draw a vertical line, these 2 points here and here have that projection. So just knowing the initial x does not determine phi naught for us, but we also know that it's moving to the left. So if it's over here, as you rotate, you go from here to here, so your projection would be moving this way. That's to the left. If you're here, you're rotating again counterclockwise. Your projection is moving toward the origin, is moving to the right. So we don't want this. We don't want the bottom point. We want the top point. All right? So that's phi naught. All right, so what is it? Well, it's cosine, right? So if, let's say, x of t is a cosine omega t plus phi naught, we know that x of 0 is minus a over 2. So cosine, if I put 0, the omega t goes away. Cosine phi naught is minus 1/2. And then my angle would be, so here I want to have 60 degrees basically, right? So that means that phi naught is 180 minus 60, right? So if this is 60 here, that's going to be 120 degrees, which is 2 pi over 3. Notice that there's this other point whose cosine is minus 1/2, right? That's maybe, if you look at it this way, it's minus 2 pi over 3. For example, if you count from here, it's going to be 180 plus 60. So it's like 4 pi over 3. But we don't want that because we have this additional piece of information that the particle is moving to the left. Okay? So there's only this one point. You can add any multiple of 2 pi to it, but it's not going to change anything, because ultimately you're going to take the cosine or sine of this phase, and factors of 2 pi just don't contribute. That's the periodicity of your sinusoidal function. All right, so we know what phi naught is. And what is omega? Well, it's just 2 pi over t. So we know that. So putting everything together, we can write x of t is 0.1 meter times cosine 2 pi over 0.8 times t plus 2 pi over 3, right? So done with that. And then we can just plug in some numbers. So I guess the problem is asking about, what is it asking about? T equal 2 seconds. So if t is equal 2 seconds, we get x of 2 is 0.1 cosine 2 pi over 0.4 plus 2 pi over 3. So that's 0.1 cosine, let's say 2 pi times 5 over 2, right? 4 over 10 is like 2 over 5. You divide by 2 over 5, so it's like you multiply by 5 over 2. So it's going to be 2 pi 5 halves plus 1/3, which is the denominator is 6, and then in the numerator we have 17, something like this. And that's in meters. Okay, so let's go back to the solution and see how it works, to see the actual numbers. All right, so yeah, so that's the thing we had. Like, it could be plus or minus 2 pi over 3, but because it's moving to the left from this picture of the circle, the plus one, 2 pi over 3, is the right answer. Our omega we can calculate is 2 pi over t, and then we just plug it into this. All right, so let's see. All right, let's simplify this a little bit more to just see what's happening more easily. So it's 0.1. So I can write this is as cosine of 2 pi. Here I have, 17 is 18 minus 1, right? So that's 3 minus 1 over 6. So factors of 2 pi don't matter, so that 6 pi goes away. So this becomes cosine of minus pi over 3. And cosine of plus or minus an angle is the same thing, so that's pi over 3 here. Pi over 3 is just 60 degrees, so it's going to be, if that angle is 60 degrees, its cosine is a half, so this is going to be 0.05 meter. And it's over here, so it's to the right of the origin on our circle. And then we can immediately, using this visualization, we can answer the question, like, which direction it's moving. It's moving this way, so it's moving again to the left. It's moving toward the origin, right? As you consider this counterclockwise rotation and look at the projection a little bit later, the particle is here, so its projection is here. So moving to the left. If you wanted to calculate the velocity, again, it wouldn't be difficult, right? So what we would do is we say, well, v of t is minus a omega sine of omega t plus phi naught, we just established that this whole thing, that phase omega t plus phi naught, is going to be over here. So that's equivalent to pi over 3, right? And we solve for omega, we know what it is, so you can just plug it in. And you see sine of pi over 3 is a positive number. This negative sign means that the velocity is to the left. It's a negative number. All right. So that was a good example to get some practice. It's kind of unfortunate that there is no figure. I think these problems are much easier to solve if we draw that circle all the time and consider that counterclockwise rotation and see what happens to the projection. All right. Okay, so here's a quick check question. So take a few seconds, pause the video, see what you think. All right, so let's go over this problem together. This is a position graph of a mass oscillating on a horizontal spring. We want to know the phase constant phi naught. Okay. So what can we say? So initially, it's at x equals 0, right? So let's say, example, xt, it looks like this, right? So we know x of t equals 0 is 0. That means that cosine omega times t equals 0, which is 0 plus phi naught, is 0. All right, so going into the circle, 0 distance on the x-axis from the origin is the origin, and we have 2 points here and here where the cosine is 0. So one of them is, this is pi over 2, right? From here to here is 90 degrees. This is going in the opposite direction, so this you can think of it as minus pi over 2. Again, everything is modulo 2 pi, right? You can think of this, instead of minus pi over 2, you can think of it as 3 pi over 2 as you go the other way. But that's just a factor of, that's just adding a 2 pi. So because these are phases and we're only interested in their sines and cosines, those 2 pi's do not matter. All right, so if that's the case, now we have to see which one works. So we need more information, and that's the sign of the velocity, right? So it's moving to the right. So x is going to be positive, right? A little bit after time t equals 0. This is moving up, so that's in the positive direction. So considering the counterclockwise motion, this one a little bit later will be here. So that should go to negative x. But this one goes over here, so that's positive x. And the correct answer should be therefore minus pi over 2. And that is the correct answer because of this visualization. So yeah, so knowing the initial position and knowing which way you're moving, whether you're moving to the right or left, or the sign of the velocity basically determines our phi naught. What about this one? So again, pause the video, take a few seconds to decide what the correct answer is. Now, similarly, this is again a position graph. And we know that initially at t equals 0, it's at minus a, right? So we know the cosine of phi naught is minus 1. And if you're all the way at minus 1, I mean, you can only go one way, right? You can only come back because you can't really keep going. That's your amplitude. So there's no new information in the sign of the velocity. And where is the cosine minus 1? It's at pi. So yeah, so that's the correct answer. So you will see, because there's only one point on the circle, right? So if you go all the way here, length, let's say minus a here, typically when we're somewhere in the middle, we draw a vertical line and that crosses the circle at 2 points. But 0 and pi, these 2 points are special, right? So there's not going to be 2 different points, there's going to be just 1 point. And then the velocity is actually 0 there. So there's really no new information in the velocity, and we find the correct phase. Okay. Here's another one. So now we have a more physical picture. So it shows us a mass on a spring. It's performing simple harmonic motion. And we want to figure out the phase constant. No, the question is, so for which one the phase constant is minus pi over 4. Sorry, this minus is kind of attached to the equal sign, but yeah, so phi naught is minus pi over 4. Okay, so again, take a few seconds. I think it's helpful to draw the circle and try to decide which one is correct. All right, so to answer, we know that the phase constant is minus pi over 4, so we draw a circle. We put a point at minus pi over 4, like this, right? It's going to be here, going counterclockwise. So first we see that the x is positive. If this is 0, it's going to be over here, right? The projection is to the right of the origin. So A and B are out. And then if it's moving counterclockwise, it's moving away from the origin, right? It's getting closer to this point, to angle 0. So the direction of the velocity is to the right, it's positive, and therefore C is the correct answer. All right, so the next thing we want to talk about is energy in simple harmonic motion. So far we just talked about the kinematics of simple harmonic motion. So let me go back to the notes here, and let's think together about energy in So it's helpful to consider an example of a mass on a spring. So in 161, you saw the expression for the energy stored in a spring that's stretched, right, by some length from its natural length. So we had we knew that the force of an ideal spring is proportional to the displacement, to how much it's stretched or compressed. So first, that we knew that F is minus kx, and that's the spring constant. K is the spring constant. So for example, if you have a spring whose natural length is here, and you pull it by some length x to this point, it's going to apply a force in the opposite direction to this mass, for example, right? It's stretched, so it's pulling back whatever it's attached to, and the magnitude of the force is just k times x. So from energy work considerations, we figured that if you're at that amount of stretch, x, and then you stretch it a bit more, so you go from x to x plus dx, well, you stretch it by another infinitesimal dx, so your position becomes x plus dx. Then the force of the spring is doing negative work, which is minus kx, which is the force times dx, right? Force times displacement is the work. And suppose you've stretched your spring from 0 to L, right? Then the total work is going to be an integral from 0 to L of minus k x dx. Integral of x is x squared over 2, so that's minus k L squared over 2. And therefore, the potential energy that's stored in the spring is going to be minus that, so that's k L squared over 2. So as you stretch or compress a spring by some length L, you store potential energy equal to k L squared over 2 in that spring. And then, once you, for example, let it go, if it's stretched or compressed, it will move away, right? If it's stretched, it will pull that object toward the equilibrium, and it converts the potential energy to kinetic energy. Okay. So energy conservation should say that there is no friction or anything like that. Should say that Q plus K is constant. Right? So let's check this for the simple harmonic motion. We know, let's say x of t is a cosine omega t plus phi naught. And we can just call this whole thing, call it the phase field. So that's the cosine of the phase, which is some linear function of time. And v of t is minus a omega sine omega t plus phi naught, which is minus a omega sine of phi. So x looks like cosine, all right, something like this. And so let's say that's x. V looks like minus sine, right? There's a negative number in front of a sine, so it will look like that. It's a derivative of this. So here it should become 0 again, right? So here it's the maximum. So it's something like this. Again, here it becomes 0. Here it's the maximum. So that's V. Qualitatively, it looks like that. And now thinking about U being 1/2 k x squared, and k, the kinetic energy, being 1/2 mass times V squared. Kinetic energy is proportional to V squared. Potential energy is proportional to x squared. So if I draw, let's say, the potential energy and the kinetic energy, first let's just draw the kinetic energy. It's like this thing squared. So again, when this is maximum, it has a maximum, then when it is 0, it becomes 0, and then it turns here, right? So it changes sign. So again, this is here. The next one is going to be here. It goes up and down. And when the potential energy is the maximum, the kinetic energy is 0. When the kinetic energy, so let's say that's U, you can imagine this being time qualitatively. And then K, the potential energy, does this, and their sum is expected to be a constant, right? So that's K. So for example, we expect U maximum right here. The maximum of U occurs when the kinetic energy is 0 to be equal to the K maximum, the maximum of kinetic energy, which occurs at this point at the top, plus 0 for the potential energy, to be equal to U plus K for some arbitrary point in the middle, maybe, I don't know, somewhere here, this plus that. So what can we say about U maximum? Well, what is the maximum displacement? It's 1/2 Ka squared, right? Our motion, remember, goes between minus A and A. So the maximum length squared is A squared. K maximum is 1/2 1/2 times mass times V maximum squared. And we had the maximum of V to be equal to A omega. So this is going to be 1/2 M omega squared A squared. And these two things are the same, right? As we said, and if we have energy conservation, which we do, because there is no friction in this system, the maximum potential energy must be equal to the maximum kinetic energy, because when the potential energy is maximum, the kinetic energy is 0, and when the kinetic energy is maximum, the potential energy is 0. So this implies that 1/2 K A squared is 1/2 M omega squared A squared. Canceling out 1/2 and A squared means that omega squared is K over M, dividing also by M. So we found that there is this relationship between omega, the spring constant, and mass, right? So if I know the spring constant and the mass of the object attached to it, then the spring constant is really the ratio of the force, of the restoring force that wants to bring back the oscillator toward the equilibrium position by its displacement, right? So the ratio of this spring constant to the mass determines omega. Omega becomes the square root K over M, right? And omega, as you remember, is 2 pi over T, right? So when omega is large, it means you have a lot of cycles in 1 second. So the time of one cycle is small. Things are moving faster, right? And it makes sense that, you know, if the mass gets larger, you have more inertia, right? So you're going to get smaller accelerations for the same forces, and that slows down this type of dynamics. If k gets larger, it means you have more forces for the same displacements. That gives you larger accelerations because F is equal to ma. So that speeds things up. So kind of it's a very sensible result. So we can solve a few other things. So using this, for example, we can solve for the period and say the period is 2 pi square root m over k, etc. All right. Okay, so going back, this shows the kinetic energy in green as a function of displacement from the equilibrium position. So when it's at the turning points, the speed is 0. It's turning back, so it has 0 kinetic energy. The kinetic energy becomes the maximum at 0 displacement at the equilibrium position. That's where the potential energy is 0, and the potential energy is going to be maximum at the turning points where the kinetic energy is 0. And the sum of these two is a constant. That's the total energy E. This is the figure we just drew in the notes. So again, potential energy goes between 0 and its maximum, which is the total energy. Similarly, the kinetic energy does the same. And we see when the displacement is 0, we have the maximum kinetic energy, 0 potential energy. When the displacement is at its maximum, we have maximum potential energy and 0 kinetic energy, and that's the sum. All right, so take a few seconds, think about this problem, pause the video, and then please come back so we discuss it together. All right, so we have a block that oscillates on a very long horizontal spring. And this shows the block's kinetic energy as a function of position. What is the spring constant? Okay, so how should we approach it? So we know the amplitude, right? We know that the kinetic energy is 0 at x equal 2 and minus 2 meters. So the amplitude is 2 meters. Okay. And we know that the maximum kinetic energy is 8 joules. So remember, the maximum kinetic energy occurs at the point that the potential energy is 0, at x equals 0. But that's equal to the total energy, because total is kinetic plus potential. And in particular, that's equal to the maximum potential energy as well, because the maximum potential energy occurs when the kinetic energy is 0. So, but what is the maximum potential energy? It's 1/2 k, the spring constant, times a squared, the maximum displacement squared, right? It occurs here and here. Going back to this figure, you see the maximum potential is at the amplitude. So we're going to have 1/2 k times a, which is 2 meters squared, is equal to 8 joules, right? So 2 squared is 4 times 1/2 is 2. Therefore, 2k should be 8 joules, and the correct answer is 4 newtons per meter. So that's the argument, right? So we know the total energy is the maximum kinetic energy, which is 8 joules, and that's equal to the maximum potential energy, which is 1/2 k a squared. So we just, knowing a, reading off a from here, which is 2 meters, and the maximum energy from here, we solve for k. All right. So this is again a slide showing what we already derived, setting k max equal to u max gives us the angular frequency, the frequency, and the period as a function of k and m. So these are important relationships for simple harmonic motion of a mass on a spring. Okay, what do you think of this one? So again, pause the video, read through it, try to find the correct answer. So you have this mass oscillating on a horizontal spring. We know the period is given to us, the time for one full cycle. And if the amplitude of the oscillation is doubled, so how would we double that? Well, initially you pull the mass away from the equilibrium position by some length, and then it has zero velocity at that point, and we let it go. So how much you pull it away, that initial condition, for example, sets the amplitude. But the question is, so if you double the amplitude, how does the new period change? Well, remember, we just calculated the period. It depended on k, the spring constant, and mass. It did not depend on the amplitude. So the answer is C. It doesn't depend on it. It's kind of interesting though, right? So you pull it more, so it seems it's traveling longer distances. So why does it take the same amount of time? Well, because it's going to move faster, right? Because the acceleration is proportional to the displacement. And as you pull it away more initially you're going to give it much bigger accelerations. All right. This is another problem, again, checking the relationships to derived. So again, do the same thing, try to find the correct answer, pause the video. So what can we say here? Say if a second identical block is glued to the top of the first block, what happens to the new period? Okay. So what happens? So if the mass is doubled, right? Remember, omega was square root of k over m, right? Omega is an angular frequency. You go faster if you have a larger k or if you have a smaller mass. So the square root of the mass goes into the denominator for omega. But omega is inversely proportional to t, so t will be 2 pi square root of the mass in the numerator divided by square root k, right? So again, that makes sense. If you add more mass, you slow things down, you increase the inertia of your object. But the dependence is, of course, as a square root. So if we double the mass, we should multiply our period by a factor of square root 2, which is close to 1.4. So the correct answer is 2.8 seconds, approximately. All right. Here's another one. So today we're doing lots of these quick check conceptual questions. So two identical blocks oscillate on different horizontal springs. Which spring has the larger spring constant? Okay, can take a few seconds and try to figure this out. Okay, so we know the blocks are identical. We know the masses are the same. We want to see which one has a larger k. Okay, so what's the information we can extract from this graph of position versus time, right? So first, we see that the amplitude of the red one is smaller than the blue one, but we figured that the period doesn't depend on the amplitude. There's no direct relationship between amplitude and the spring constant. So the amplitude is just set by the initial conditions. So that's not very useful information. The other thing we notice is the distance between the peaks as a function of time for the blue one is larger, right, than the red one. So the blue one has 1, 2, 3, 4 peaks. The red one has 1, 2, 3, 4, 5 peaks. So it has a smaller, the red one has a smaller period. The time, this difference between the peaks is shorter, and it has a higher frequency. Okay. So the red one has a higher frequency, higher omega. Omega was square root k over m. M is the same because the blocks are identical. So the one with a higher k, higher spring constant, which is the ratio of the force, the spring applies more force for the same displacement. The one with a higher frequency, which is the red one here, must have a larger k. So that's the answer, right? So we know that the frequency is proportional to square root k, and clearly the red one, it has more cycles in the same amount of time. It has a higher frequency, a shorter period, should have a larger spring constant for the same mass. Okay. So this is another example. So let's read through this together. So we have a 500 gram block on a spring, is pulled a distance to 20 centimeters and released. And there are oscillations, and we measure the period. Okay. So the question is, at what position or positions is the block's speed 1 meter per second, and what is the spring constant? Okay, so I think this is a good place to stop. So the hint, of course, there's using conservation of energy at the top. So so try to use energy conservation to solve this problem, and we'll start the next lecture working out this problem together. So it's, you have the mass, you know the amplitude, right? It's 20 centimeters. You pull it by that distance and then let it go. So that's the maximum displacement. And you measure the period. You just observe, how long it takes for it to come back to where it started from. And so we want to find the position or positions where the block has a certain speed. So a hint is, again, the speed is related to the kinetic energy, and the total energy is conserved. So try to work on this problem without looking at the book, and then we'll go over it in the next lecture.